some of the students, some of my, okay, yeah, warning, warning, you're live on the internet, things you say you can't retract. Papangulo. I didn't say that correctly, but I'll get better at it when I learn. The first thing you need to learn in any language is how to swear and how to order beer. And then you go from there. What were we going to do? We're going to do eigenvalues and eigenvectors, but I wanted to show that I have more than one talent and I need money. I'm not going to beg, but I think I just did. I made a mistake, but just keep going. Let's start. That was Isle of the Flightless Birds by 21 Pilots. It's the only one I can remember off the top of my head. I haven't played that in a long time. And please cut your nails, otherwise it doesn't work so good. What was I going to do? I was going to pretend I knew about eigenvalues and eigenvectors. And then I was going to, choke on my own words, quite literally just there. And then describe... this is what science and math is, I think. It's a dialogue and it's a conversation ongoing with multiple participations. And hopefully when I do this in the correct way, pedagogically and not pedantically, it actually strikes out conversations and makes people want to go learn more, which it always does with Tim, which tickles me in a special way in my heart. Because we started talking about eigenvectors and talking about it in a sophisticated PhD type setting instead of first year setting. And then he went and tried to trump me and talk about power method, but I have this in the appendix of my PhD. And then I realized I don't even have my PhD on this current laptop. I don't know where my PhD is. I don't really care either. But I have most of it in my memory still. So let's talk about the power method and this dominant eigenvalue to compute dominant eigenvalues. So then I can spit up and hopefully talk about an hour's worth of stuff just by doing this, and then I'll fake it till I make it. And then we can talk about and then you realize that it's also not, people phrase it this way too, and they're like, oh, adding fractions, that's such grade 2. And it's like, well, come up here and add some fractions right now. It's like, oh, how old are you? And you can't do it. So is that really a grade 2 subject? There's no age limit or age restriction on love. I mean, on mathematics. That was Freudian. So there's no age restriction. And how about when you're 20, you revisit the fractions? Because instead of memorizing the thing that they don't know how to do, and if I have this type of thing, so let's start off with that. Let's do that where it's the same first of all. If you have the same denominator and I cut a pie into 3 pieces and you say I get 1 of that, and then I cut the pie into another 3 pieces and I say you get 2 of those, you can clearly see that I get the same amount of pie. And I draw a picture. So if the denominator is the same, it's just this was the rule over b, right? And then what do you have to do? I'm going to reduce general fraction adding to this case. And how do I do that? I get a common denominator. But the trick always, which I'm going to do in a different context to do dominant eigenvalues, is multiply by 1 in the form of something over something. So now if it's a over b plus c over d, you're like, I don't know what to do. And they tell you, I've taught these people. I have to teach the class which teaches the K to 12 people how to teach the other math classes, and they don't do very good. So I've seen what they're trying to teach los niños. You can do the kids in Italian, the little kids in Italian. But what is it going to be? Yeah. It's going to be AD plus BC over BD. And then you're trying to remember that formula and you're like, that's so many moving parts and it seems foolish. What's this one missing? I want to reduce it to this case. So this one's missing D. So I multiply by 1. And then this one's missing B. And then the formula falls out. There's that guy. And there's that guy. And then BD is the common denominator. And the way to view that is If now that my mom used to consistently make me share with my brother, but I'm bigger than him, so get out of here, Stuart. I'm not sharing with you. Oh, fine. She said it. I'm gonna you're giving that back when she leaves the room. And then what if you cut it this way? And then what if I say you get 1/3 of this and then 2/4 of this or 1/2 of this, and then we're adding, and then it's different. Do you see how to do this geometrically? First of all, I like the geometry much more, but this is, I get 1/3 plus 2/4. Let's call it 3/4 so it's not reducible. Do you know what to do? Have you seen this picture? Cut it into squares so that they both have the common denominator. Oh, and then what do I get? 1, 2, 3, 4. So this one would be 4 out of 4, and this one's missing a 3. And so now I get 9 of the squares and 4 of the squares, which is going to give me 4 plus 9 over 12, which is, I get a slightly more than my brother does. Get out of here. You're smaller than me. Out of the 2 pies that I have to share. Plus the pies are usually not. This is meatloaf, I guess. Meatloaf. 2 out of 3 ain't bad. Yeah. What's his name? Can I say that? Bitch Tits on frickin' Fight Club.
Oh, yeah.
Yeah. Yeah. So first of all, there's that. That was adding fractions, but then my point was there's no age to this. And what we're going to start doing in my linear algebra class, which they made me teach 3 times in a row in the same day this semester, I have to view this slog of a task, and I still have to enjoy myself and get enthusiastic and put game face on. And how do I do that? I do it vicariously through the student's point of view. I know that you've never seen it before, so I'm going to get excited about it. But when I talk about eigenvalues, it can go from first year eigenvalues to PhD type eigenvalues, but it's still the same topic. It's just knowing your audience and how to talk to them. So first of all, let's go through a whole bunch of terminology, and I'm just going to spit it out on the things that I'm not going to talk about in the linear algebra class. First of all, what we're going to do is, in the linear algebra class, what is an eigenvalue? What does it do? More importantly, ask yourself. I'm going to show you how to get them and calculate them, and then once you can calculate them, you think you know what they are. But I had no idea for the first 3 or 4 years that I use eigenvalues what the hell they were doing. They're finding invariant subspaces under linear transformations, whatever that means. We'll get there, possibly today. If not, come and watch next time. It's trying to show you what maps into itself when you're trying to move things around in space. I've got a really good pedagogical example for this. Just I got to slow my roll. First of all, what is this looking for? And then we're going to stick to 2 by 2, mostly so that I can compute and not have to do this generalized eigenvector too much. And then what happens if he's not diagonalizable, et cetera, hands to the air. So let's do this for 2 by 2 matrices, but it will in general work to n by n. I've already made myself out of breath. All right, so what we're looking for is, how does this turn into linear transformations? So let me back this up. I don't know, I keep looking for it and I keep throwing it on the ground and then being like, where did I throw that? Right there, let's put it there. So a linear transformation is usually called T. From R, let's do an operator. So it's going to operate on R2. So I'm going from R2 to R2. And now the graph of that, whether it's injective or not, that was a joke from earlier, is going to be 4-dimensional. So I can't really draw this. Things get complicated really fast. So I can draw the domain and the codomain of this separately. So if I wanted to talk about the pedagogical one that I'm going to do, and we'll talk about the eigenvalues later, let's talk about a transformation which is linear. To be linear, it's going to have 2 defining properties, and there's a third property, which is the easy one, which will be the contrapositive is what you use to show that it's not linear. You never use this one to show it's linear. But this is how I know this is a lie your whole life. This is not linear. This is a affine transformation. It's only linear if b is 0, because it has to map 0 to 0. And if b is not 0, it doesn't map 0 to 0. So this is not a linear transformation, it's an affine transformation, Mark would say. The 2 defining properties, which you can make as 1, but we'll take it easy, is that t of lambda x has to be lambda times t of x. I'll use lambda specifically because that's going to be our eigenvalues. And then what I want is it has to be split sums. Our 2 we have scalar multiplication and then a vector addition, and it has to preserve these. We would call this a homomorphism. not an isomorphism. It has to be injective and surjective to be an isomorphism because it's going to preserve the structure linearly. This could be from different dimensions possibly also. So this would be in R2 now, this addition, but then this has to be t of x plus t of y, which will now, this sum is now in 3 dimensions because it's in the codomain. Oh, how do you make that 3-dimensional? With great pain. So there it is. So if I'm going to do that kind of thing, what we're saying is if I add the vectors in 2 dimensions and then apply t, that should be the same thing as applying t and then adding them in the codomain. It has to preserve the linear structure of both vector spaces. These could be arbitrary vector spaces eventually too, but we'll tone it back because we're trying to do first-year linear algebra, and this is, I have to live with the whole thing inside my head. You just get glimpses of it. And then once you have this, you can use these 2 properties to prove a theorem that says you must map 0 in dimension n into 0 in dimension m. Or if we're going to operate on R2, t of 0 has to equal 0. So what the theorem says is if t linear, then t of 0 is 0. And then people want to say that if I define t of x just in a single variable as x squared, hopefully you know that that's a parabola and that's markedly not linear. But does it send 0 to 0? Yes. I'm never going to use the fact that it maps 0 to 0. T of 0 is 0 squared, which is 0. And then therefore I can say that this is a linear mapping? No. It's the contrapositive. The test for divergence is an analogy. It says it in the title. Don't use test for divergence to say something is convergent. What are you doing? I'm going to use the contraposit. Yeah, what the hell? It says it in the definition, in the statement. Tim's liking this. So yeah, if t of 0 is not 0, then not linear. You use the contrapositive to break an invariance under something. So that's how you would use the easy scenario to say that something's not linear, but I never use it. It's a priori assuming that it's linear, that you know this already, which means you've checked these 2 things. I'm going somewhere with this. I don't know where. Hell possibly, but not today, Satan. So this is an operator, and then I want the special kind of operator which maps 0 to 0, which you can use as a conclusion. And then what I want with this is there's another theorem which is going to say if it's biconditional actually, which is A implies B and B implies A. T is linear if and only if there exists a standard matrix T which says that linear mappings and matrices are the same thing. And this coincidentally is, you can see in the non-commutative scenario, we say A times B is not equal to B times A. But if those are linear mappings, this has to say that F following G can't equal G following F, which makes sense because this is, if these are both linear maps, F following G won't equal G following F, and A times B is not equal to B times A, which will be the matrices of the composition of 2 linear transformations. I can't read what people are putting in the thing because I'm looking at something else. There's people commenting. Oh, Jasper the horse is here. If you think that you're the first person that's tried to, if you think I've gone MIA with just you.
Like, it was like several weeks where it was like me and Tim, are you alive? You know, what's happening?
You'll know. How long did it take for them to find Lane Stanley? It took 2 weeks. Sad and alone. I knew you'd show up here eventually. I don't have to, and I don't really care at this stage whether it just means at least someone out there cares if you filed a missing persons report.
Well, thank you, Jasper.
Yeah, thanks. I turn off my notifications and then I forget to turn it on is what I'm going to say live on a stream. What was I doing? Hi, Jasper.
Everybody's got to go silent every now and then.
How was the potluck? Was it successful? He had a potluck yesterday, and he offered and invited me over several times, and I didn't text him back, nor did I go yesterday, nor did I text him this morning when he said, "Are you okay?" That's the real. I don't. Yeah, this is. If you've met me, fuck. When we start hanging, or frick, when we start hanging out, you'll see. I can barely pay my bills, let alone afford gas or a meal to go to a potluck. Is the true story. If I'm being honest. If I'm being honest, are you usually not honest? Well, the problem with the world is that it's full of liars. You need to differentiate between the liars you can trust and the liars you can't. Yeah, yeah, yeah. I stole that from a movie. I'm not giving any credit. George Carlin. It's not all fucking fancy fucking comedy. This is, yeah, commentary on society. I'm not trying to compare myself to George Carlin.
To say that George Carlin was the modern Greek comedian later.
Yeah,
Oh, absolutely.
yeah.
Yeah, because his comedy and 2,000-year-old Greek comedy.
His one is about God and the monetary. He's like, he's all knowing, he's all seeing, but money, he doesn't fucking get it. It's like, I don't know. All ambient, all freaking benevolent, all seeing, all knowing, but money, he doesn't know it. You need to send me.
God didn't create money.
Yeah, you need to send me more. I don't understand. Well, which is also philosophical. That's saying the axiom that axiom 1, God exists. Axiom 2, God can do anything. This can't be true, because if I use axiom 2, then I can say that he can make himself not exist, but that contradicts axiom 1. And if he can't make himself not exist, then there's something he can't do.
Right about now, we should be playing the Philosopher's Song from Monty Python.
Immanuel Kant was a real peasant. He was just as lost as Hegel. I was a boozy beggar. I drink, therefore I am. I can sing it. I used to watch that religiously. Oh, pun intended. All right, what was I doing? So, thanks for showing up. I knew you'd show up when I made a live stream because you had me on notifications, Jasper. Oh, pee pee poo poo. Oh, yeah. Excellent. Thank you. Thank you. You can leave now if you want, or you can see that this is the fun that we kind of have. This student came up at McEwen today and made me do a survey about the vendors. I like you. You're friends with us now. And I said, just show up and say pee pee poo poo, and then you can leave. And then he did. A man of his word. Thank you. Go enjoy your Friday night. I don't know why you showed up to a math stream, but we're gonna have some fun. I'm not talking to myself. I swear, there's 2 other people in my basement. Oh, they can hear you? Oh, I didn't know if you plug in the microphone or not. I can hear you, but I hear a lot of things. Are you? Yeah. What was I doing? Okay, if t is linear, if and only if it has a standard matrix, which we're going to call this. So now this is where I start, and then matrices have eigenvalues. So technically speaking, t has a kernel, and this has a null space, but they're the same thing. What maps to 0? Null in German is 0. So now we're going to associate, we can drop the linear mappings, but from a linear mapping, there has to be an associated matrix to this. So now let's talk about a linear mapping specifically, and let's just build it because I like to do this, and Mark Solomonovich did this. We'll do the demographic of linear transformations in the plane, and then in a yaw, pitch, and roll are all linear transformations in 3 space, which yaw is, roll is that one clearly, pitch is this one, and then that one's yaw. Yaw! Yep, yaw! All right, so if we're going from R2 to R2 in T, and I want this, let's just say it in word land, and then we'll say it in vector land, and then we'll do it in standard matrix land. So if I want T to be reflection orthogonally about the x1 axis, then I have to look at this guy, and then I have to look at the pre-image over here. It's better to do it on 1. That's why they map it onto 1. So I'm doing this. But if this is my pre-image, the pre before I apply it, I'm just going to call it x1, x2, because it's 2-dimensional and it has coordinates. Where do you get your coordinates from? From the linear combination of the ambient bases in dimension 2, which is any 2 non-collinear vectors. Once I have coordinates, I want to move them around with t, which is going to be chapter 5 that we do in my linear algebra class 3 times every day. Where's it going to go? x1 didn't move, did it? That's x1. But now I'm going from x2 to negative x2. So I can just build what it's going to look like. So that's going to go to this image of x1 negative x2. So now I have the algebra. That says t of x1, x2 is equal to x1 negative x2. And now Tim knows for sure, how do I find the standard matrix? The standard matrix is going to be the image of that linear transformation on the canonical basis vectors E1 or E2, which we normally call I and J in 2 dimensions, but I'll keep the notation for extending this to beyond 3 dimensions. Or the way that I view this is, if we say that linear transformations are matrices on the left, it has to be on the left. I just say, remember your Beyonce, to the left are your things. Oh, there's a joke in there, I'm going to suppress it.
Should we good? Speak?
Yeah. Are we good?
Yep.
Mic check, 1, 2, 1, 2. Roll right. No one listens to Bulls on Parade anymore. That's a good album. Da-na-na-na-na-na. Da-na-na-na-na-na. So what I viewed is, how do I do matrix multiplication? It has to be 2 by 2, and then it has to be 2 by 1, and the inside indices match, so the outcome will be 2 by 1. Matrix multiplication. But now I say to myself, what in the first row, this entry is going to be the dot product of row 1 with column 1. So what do I have to multiply in this row to have there to get an x1? I need a 1 and a 0. Because this times this will give me x1. And then this is complex conjugation also, because complex conjugation takes you from z to z conjugate. That was a little bit too much. I shouldn't point that out, but that's how my brain works. So what does the matrix of complex conjugation look like? What do I have to multiply to get negative x2? This. So there's the matrix for complex conjugation. But this is reflection about the x1 axis. So now I have the standard matrix of T. And now I ask myself, where we're going to lead in finally to eigenvalues and eigenvectors. That's an old man grunt because I have an extremely sore arm. Loading a double bass into freaking the car after my daughter's show at the Jubilee Auditorium. The Northern Alberta. The Northern Alberta Jubilee Auditorium implies that Calgary has one too. Who cares about Calgary? Shots fired. Yes, and a chauffeur, and I keep trying to say that I'm not either, but my daily tasks seem to tell me different. What was I doing? So now the standard matrix, as promised, of this is now I have a matrix. But do you see where I'm going to say that it's invariant subspaces under linear transformations? So we're going to call this A. And in 2 dimensions, this really looks nice. Because if I say that the definition of an eigenvalue is going to be if I take A and hit it with X, which is the same thing as doing T of X, because they're the same thing now in this identification. I want this to be what? What does that say about the span of X? When I apply T to this, it's going to map into itself, which is the span of X. because the span of x is all lambda x such that lambda is a real number. All possible linear combinations of this. We'll start off with lambda being real. It can be complex, but you really want to do this over the complex field, which is the algebraic closure of R, which means all the roots are in there. So, but what does that say? That says when I apply t or a to x, it maps into its own span. And so which vectors are going to do that? And what are the eigenvalues? I'll catfish you for a little bit and then we'll see. But that's what I'm asking really in an eigenvalue problem. And because I have ax equals lambda x, what I'm going to do is move this over, and then I'm going to write this as if and only if ax equals or minus lambda x equals 0. And then why did I leave a space there? Because I can multiply anytime I want by the identity matrix. And this has to be a priori, this is not 0. So this is going to help us in a second. And then what does this say? I can factor out x out of both terms. So then I have a minus lambda I x equals 0. But x is not 0. So a minus lambda I has to equal 0. And that will be if and only if the determinant of a minus lambda I is equal to 0. Is that the same thing? People are like, I like it more when it's lambda I minus a. Is that the same thing? Yeah, it is. I'll show you. This is the determinant of, you're like, I want a negative there so I can flip this around. There's two negatives there. Negative a minus lambda I equals 0. And then what is it going to be? Oh, I'll get you there too. But now I can write that as if and only if the determinant of negative lambda I minus a is equal to 0. And what does that equal if I take it out? Negative 1 to the n, which is the size of the matrix. Every time I take it out of a row, I get that multiplication. Careful. This was on your homework 3. Times the determinant of lambda I minus a, but that's equaling 0, and then I can cancel it because negative 1 on both sides will still equal 0. So do you see? It doesn't matter whether I use this definition or this definition, but I and Mark like this one more because then this creates a monic polynomial it's called the characteristic polynomial, and it is a polynomial for every n. But let's see now. So what is the definition condition of being an eigenvalue and an associated eigenvector, which is an eigenpair? You'll get old and make man grunts too. Son of a bitch, my arm hurts every time I do it. Stop doing it. You go to the... Okay, yeah, I know. Oh, the leg one has been working quite well.
ASMR, if people will pay money for ASMR, they'll pay money to listen to some old dude grunt.
And if I'm grunting properly, it won't be putting you to sleep. Wake up. Wake. Yeah. I want to say several things, and I'm not going to. Oh, I am learning because Tim and Lorenzo have politely asked me to please shut your dirty mouth because I want to monetize, not because you just tried to step on me and compel me by law and the government. Yeah, I could give a shit. I poop about that. Poo poo pee pee. See you later. Did he leave? Say thank you. Bye. Is he still here? Anyways, we got a new follower and he commented. So then, yes, this will help us out. Now what? So ax equals lambda x if and only if the determinant of lambda I minus a is 0. And this is called the characteristic polynomial, char poly. And that's how you're going to find the eigenvalues. And then what you're looking for is the kernel of the linear operator, but not the kernel of the operator. It has to be the kernel or the null space of lambda I minus a will give you the eigenvectors associated to the eigenvalue. We can do this in a second. I will for this one. But what is it really saying? I wanted to point out also as we do this. So first of all, let's go back and use this one and find the eigenvalues, and then we'll see what's happening. Do you see what's happening yet? Who doesn't move or maps into his own space when I try to move across this? Well, anything horizontal won't move at all. So one of the eigenvalues is going to be 1, and I will be the associated eigenvector or the basis of that linear span. Anything in this direction won't move at all when I try to move across it. And what's the other one that won't move? You'll move to your negative if you're vertical completely. It's only when you're not vertical that you will get mapped into some new vector, which won't be invariant. But this space, the vertical space, will be invariant under this linear transformation, and this space will be invariant under this transformation. So before I even start, if I know what I'm talking about, lambda has to equal 1 will be an eigenvalue, and lambda equals -1 will have to be an eigenvalue, which they will. And then the associated eigenvector is going to be 0, 1, which we normally call J or E2. And this one has to be the associated vector 1, 0, which we're going to call I or E1. I know. Watch it happen. Watch it happen. Ah. It doesn't get old till you can laugh. If it makes you feel any better, I'm a pedantic kid, but every time I do that, it really, really is hurting me. So you can take pleasure in that if you want. Okay, business. Lambda I minus A. Also, if you notice on your first midterm, what did I make my students calculate? Lambda I minus C. Oh, catfish. This is an eigenvalue problem already, but I just didn't tell you. The lambda was a 2, but that means 2 was an eigenvalue of that matrix. Shh. All right. So here's A. What are we going to do? What's lambda I look like? This, which means it goes on to here and it's a diagonal matrix. So lambda, lambda, 0, 0. And then if I want what's A look like this? So lambda I minus A in this case is going to be what? Lambda minus 1, 0, 0, lambda plus 1. I've also picked this for simplicity so that you can see what's going to happen with this. And then this is also a diagonal matrix, and I'll show you what we can also do with this in a second and give an application, not your silly Lagrange multipliers, because I don't know how to do that. I like your confidence, but I don't know how to do everything. My limit of knowledge is tending towards infinity as time progresses. It's an asymptotic limit. All right, so what does this say? And then now I want the determinant of this, which how do you make that into a determinant? Take away the little ticky things, and then now determinant, which is what? Do you see? Lambda minus 1, lambda plus 1. I'm trying to factor this. Please don't expand that. I want to know, when is this equal to 0? Guess what it is? I told you when we started, lambda equals +1 and lambda equals -1. This is the dominant eigenvalue, but it's not unique in this scenario because the modulus of both of those guys is 1. So this one is also, there's not a unique dominant eigenvalue, so it won't converge very well when we use the power method. We haven't even got there yet. We're probably not even going to talk about the power method this time. Oh, do we have pre-roll? I don't care. I just realized that we had a pre-roll counter. I'm like, when did that start happening?
Been there since the beginning.
Okay. I'm not stopping. You can yell at me to stop.
We just post on YouTube anyway.
Okay. Yeah. It's Friday, and yeah, the only reason I got them to come over is because I'm sad and lonely, and I want company on a Friday, because I think they're slowly going to ruin my life right away. You can get...
Same they in that sentence. Let's be clear.
The they is actually a plural. Yeah, not the same they. And it's an actual plural. Oh, that's probably why that's why they are canceling me. Bah. So let's use lambda 1 equals 1 and lambda 2 is equal to -1. Those are my eigenvalues. Let's smart. How do you move this when you don't want to move your arm? Move your body. I did that all day today because it's like, oh, I don't want to move my arm so much, so I'll just move my whole pivot. Those were the diagonal entries. So how do I find the eigenvector associated to this? I shouldn't have erased it, but it's lambda minus 1, 0, 0, lambda plus 1 is lambda I minus A. Now you put that lambda in here, which also Lorenzo actually won last time because it was a non-trivial guy because it had the spectral radius and the beta to the 1/3 and all that kind of stuff in here. But this is what I'm saying again. We're going to look for, put the lambda in there, and then I'm looking for the null space of lambda I minus A, which is this equation. It's a homogeneous equation of this. And one of the rows has to be 0. This is so simple because I picked it on purpose that it's just going to give us the row of zeros immediately. So when I put 1 in there, I immediately get 0, 0, 0, 2 equals 0, 0 is the correct way to do it because I'm looking for the null space or the kernel of lambda I minus A. And then I can divide this trivially by 2, and so I get this. And so what does that say? Do you see? Who, first of all, in my class, I just did it more than once today. How many leading ones do I have? 1. And which column now is the free variable? The one that doesn't have the leading one. So lambda 1 will be free to be anything. This says lambda 2 is, or this says v2 is 0 and v1 is free. And so what does my vector look like? I told you it would be t0 or the span of I. I is the vector, eigenvector associated. You can pick whatever value you want for t, but I'm going to pick it to be 1. And so what that says is lambda 1 equals 1, and the associated eigenvector is I, 1, 0. Okay, good. Now let's do the same thing for negative 1. I put that back into here. But now what's going to happen? I'm going to get, when I do that for lambda 2 equals negative 1, I'm going to get negative 2, 0, 0, 0, 0, 0. I start sounding like Mark Solomon. 0, 0, 0. He phoned me again. I should really phone him back. I don't care. Come to my live stream. He'll never find me on here because he's a boomer. Now I can divide by this and I get a 1. And now what does that say? Now this says this will be the free variable. V2 can be 0, or W2 if you want, is free. And so now what that says is W1 is 0 and W2 is free to be anything. And the associated eigenvector W is going to equal 0t, which is 0, 1 times t. So associated to this one, I'm going to get that my eigenvector is w, which is 0, 1. And now do you see pictorially what that said? I'm looking for invariant subspaces under linear transformations. I really want to use my right hand, but I don't. Oh, yeah, that feels way better. Duh. So I like cats. Now what that says is, do you see the picture? When I'm trying to move orthogonally across this axis, what doesn't move and just stays identically the same? The eigenvalue 1 means that t of x is going to be 1x, which is just itself. It won't move at all if you're in the span of I, which is this vector. So it's invariant. It maps into itself. Invariant subspace means that you map t of the entire image of that will stay in itself. And then what maps to its negative if I move across this? Anything purely vertical, which is j, will map to negative j. And so what that says is if you are t of I will map to 1 times I, which is just I. And if you are t of j or any multiple of that, you will map to negative j, which is negative j. And so what this is really saying is when I try to move things around, what just maps into their own subspace, eigenvalues and eigenvectors. And then we want to talk about linear independence of these and decompose into the null space and the row space, column space, null space, and these types of things, which is what Shawnee wants help with later. But that'll be a different problem. So now eigenvalues, eigenvectors from different eigenvalues are linearly independent is another fact I'm just going to wave at us. Where's this? Am I on track to showing you the power series method permanently? Let's talk about, no we're not. Let's talk about a bunch more terminology about this. So, I'm not bending down for that. I'm just going to take one that's dead and take the cap off that one. Haha. So now what I want to talk about is the algebraic multiplicity of an eigenvalue lambda and the geometric multiplicity. If the geometric multiplicity of every eigenvalue is equal to the algebraic multiplicity, you're diagonalizable, which means I can diagonalize the matrix. If I do that, also, we should carry around the fact that the matrix that I created, P, was 1, 0, and 0, 1, and that was associated to the eigenvalue lambda equals 1 and lambda 2 equals -1. We're going to need that in a second. This is P diagonal P inverse, and then I'll show you why this is an application also to Lagrange multipliers, but not yet. The algebraic multiplicity is the number intuitively of times lambda divides the characteristic polynomial, divides the determinant of lambda I minus a. In this case, they were both 1. This one happened once. I only got it once as an eigen. This one in our case was lambda minus 1, lambda plus 1, which means this is to the power 1 and the power 1. So the algebraic multiplicity of lambda 1 is 1, and the algebraic multiplicity of lambda 2 is also 1, because it divides that characteristic polynomial exactly once each. We lost like half the viewers once they started talking about all this crap, which is all right. It's Friday night. I don't even know why you showed up in the first place. Now what do I want? The geometric multiplicity, geo lambda, is equal to the dimension of the span of the eigenvectors associated to this, which could be called E lambda, which is going to be intuitively how many linearly independent eigenvectors associated to the eigenvalue. Linearly independent eigenvectors associated to the eigenvalue. In this case, we also got 1 each. We got that this was V and this was W, and they become the columns of this matrix P. And then now, especially if you have two real distinct roots for this 2 by 2 matrix, the algebraic multiplicity equals the geometric multiplicity for each one, because I have one linearly independent eigenvector associated to the lambda equals 1, which divided it once. So the algebraic multiplicity is 1 and the geometric multiplicity is 1 for both of them, which says that A, which was 1, 0, 0, -1, can be decomposed into P diag lambda I P inverse. Is that right? I can never remember whether it's P inverse P or PP inverse. PP inverse. It doesn't really matter, I don't think. You can do it to flip it the other way. But why is that useful? Because this will be P was 1, 0, 0, 1, which happens to be the identity matrix, which is multiplied in this case by the diagonal matrix, which will be 1, 0, 0, -1, which is the inverse of this, which is 1, 0, 0, 1 inverse, which happens to be A. That was an easy one, Tim, because it's multiplying by this. But in general, why is that useful? Because now if this was a system of, this would be uncoupled, but if this was a coupled system of differential equations, then the general solution is e to the matrix. And e to the matrix is a matrix, but it's e to this guy if it was non-trivial and this wasn't just the identity matrix. And then what can you do to this thing? It turns out you can turn it to put it into just P times E times the diagonal matrix of the lambda I times T times the P inverse is the dirty trick. And then what does that become? It just becomes E to the eigenvalues times T, which would make sense. I'll show you when I have to erase it again. If I had, which is uncoupled, which makes it fairly non-trivial, but if it's not non-trivial, we want to decompose this and do generalized eigenvectors in block Jordan form, which is why I still didn't get to the power method, but this is an application of this. If I had x prime is equal to x and y prime is equal to negative y, then I can view this as x prime y prime equals a xy, where A is this matrix. And do you see the solution? The solution to this is e to the t. The solution to this is e to the negative t, but then I get the clever general solution for this when it's a linear system of ODEs where it's coupled and these are non-trivial entries. It still gives you a way of computing the general solution to this. So one of the applications is solving coupled linear systems of differential equations. You have to decompose it into its Jordan block form, and then you can do they call this Q for the general Jordan form. And then we have a way of computing this.
I think that's Noah.
Yeah, it is Noah. I'm tutoring him. Oh, is it already 7 o'clock? Get the hell out of here. I'm supposed to be tutoring Noah after this. He's on Eid, though. Are you still dizzy, or are you ready to frickin' go forwards with this? So, there's a good segue. Anyways, it's Friday, and they've unbeknownst to them, they've already overstayed their welcome. Wait, what? You said come over on a Friday. You had nothing better to do. Well, Tim did. I don't know why he showed up.
Alright, so on that note, are we ending?
We're going to end next time. This is the segue. Next time, possibly tomorrow, if not Sunday, I'll actually tie this into the power method.
Okay.
And I'll use the same dirty trick as, you can cut me off anytime I'm talking. You can use the same dirty trick of, as we leave, I'll just start doing it and then you can cut me off. I'm going to call 1 equal to this, but we know that v is a non-zero if it's an eigenvector, so I can call that v dot v over v dot v. There's the first thing I did. The first step into showing Rayleigh's quotient and then using the power method is I turn 1 into something over something, in this case the dot product of an eigenvector.